get started here. Now, for those of you who are using our Visual CAD/CAM product, um, your visual CAD interface is what you would be using for either creating your part profiles for turning, or you could be importing your files in from your CAD system that you're used to creating your drawings. It could be just a simple 2D profile, could be in a DXF, DWG format, or you could be importing it in as a solid model, which could be IGES, STL, or Parasolid, or any of the file formats that can be translated into Visual CAD/CAM. The first thing we will be focusing today here is the turn coordinate system and orienting the part. So the turn coordinate system is basically the top view in the Visual CAD/CAM system, which is your XY plane. So when we define a part in the turning module, we automatically take the world X coordinate and orient that to be your turn Z coordinate, and we take the world Y coordinate and orient that to be your turn X coordinate. So when you load your turn browser, turn module, you will notice that the world X coordinate is automatically swapped out with the turn Z coordinate, and the world Y coordinate will be swapped out with the turn X coordinate. So if you create a drawing or import your part and it's already in the top view, you wouldn't have to rotate the part or make any additional transformations in here. So in simple terms, your XY in the world coordinate system of the CAD is basically a turn coordinate system in here. So to orient the part for turning in Visual CAD/CAM, we need to make sure that while defining the part, we want to establish the back face of the part at the origin. And then we'll go through the steps of setting the 0 to the rightmost face, or which could be your front face, which we'll be doing that by using the work 0 as we do the programming. But to define the part in the turn module, we need to make sure that the back face of the part is set at the origin. So in this particular example, what you're looking at here, you'll see that when the drawing was created and drawn, the front face of the part is at the origin. So in order to define the part in our turn module, the first thing we want to do is we want to put the back face of the part at the origin. So this could be done in several different ways. You can select the geometry and go into the Modify Transform tab in Visual CAD and move it, or you could use the Orient Part feature in the turning browser. Now, if the turning browser is not open or displayed, you can go to Visual CAM on the menu and then select Turn, and this will display the turn browser. Now, under the Program tab in the group called Setup, you can select Part, Orient Part, and you can select the origin, and you can snap to an endpoint, or you can snap to the grid and select OK. So this automatically transforms the part. And now you're noticing that the back face of the part is at the origin. So
another, Uday, let me break in here. Another way of saying this is actually the curve or the model that you're programming should be in the first quadrant. So all the programming is actually done in the first quadrant in our lathe system. So, lathe users might be familiar with the quadrant programming. So in our system, it's the first quadrant is where we do all the programming. Thanks, Uday.
Thank you, Joe. So that would be positive X and positive Y, and basically quadrant 1 is where you would basically orient the part and place the part. So here I've displayed the coordinate system origin using the CAD, which is the world coordinates. You can see that's your world X, your world Y, and the Z is pointing towards you. So when you load the turn module and display the machining coordinate system visibility, you will notice that the world X is now being swapped out with the turn Z, and then the world Y is transformed with the turn X. So I'm going to go ahead and hide the display of the triad for the world coordinate system, so just to make it easier for visibility here. So we currently have the coordinate system established, and the part has been oriented in Visual CAD/CAM. And the next step would be to define the part. We'll define the part in here. So we go into Part, and we're going to select Turn Part. So for defining the part, you could be either working with a solid geometry or surface geometry or even a mesh geometry, or it could be just a simple 2D profile. You could have created a section of the curve. So you can click on select curve, highlight the curve. The curve could be made up of one or more curve segments. And then as you right click on it and select save, the turn part is defined. So it automatically revolves it about the axis of rotation to define the part. So to define a part in turning, you could be working with a 2D geometry like a profile, a cross section. You could also be working with a solid geometry. So the next example, we will be covering how to define a part using a solid geometry. Folks, if you do have any questions, please feel free to post those questions in the questions panel and we'll get them answered to you. So I'm going to go ahead and switch over to our RhinoCam product to go through the steps of turn coordinate system and orienting the part and defining the part for turning. So I'm going to go ahead and load a part. So I have a solid model in here loaded. And the same principles what we talked about in Visual CAD/CAM applies to RhinoCam as well. So you need to make sure that the part, the origin, which is the back face of the part, is oriented and set up along the world coordinate system, and the back face should be at the origin. So if you take a look at it from the perspective view, here we have a solid model, and the back face is at 0, 0, 0. And I'm going to go into RhinoCam and select turn to display the coordinate system. So the world X coordinate system is automatically swapped out with the turn Z coordinate system. The world Y coordinate system is transformed or swapped out with the turn X coordinate system. So you can toggle the visibility of the machining coordinate system and the world coordinate system display from the machining browser in RhinoCam Stern module. So as long as you orient the part in the world XY plane and the first quadrant, if it's just a 2D profile, or if it's a solid model, you just have to orient the center line of the part in the world XY plane. So you're on quadrant 1 and quadrant 4 as you see it. So if you had the part moved or oriented in a different space, you just need to make sure that you position it correctly using the transformation tools in Rhino, and you orient the part. So this would allow you to define the part. So any of the features that are behind the origin will automatically be ignored when defining the part. So when we go into part and you select turn part, we're going to use select surfaces in this example since we have some solid surface geometry. And you can just drag a window to select all of it. Right click or press enter to accept your selections and then select save. So once the part has been defined, you will notice that the silhouette of the cross section is automatically being displayed and your part has been fully defined, and the machining browser has been updated and shows part is fully defined. Now once the part has been defined, we can go through the steps of programming the toolpath. So we looked at an example on how we can select a 2D profile to define the part. Now we looked at an example of a solid geometry or a surface geometry to define a part in turning. Folks, if you do have any questions, please feel free to post those questions in the questions panel and we'll get them answered to you. Now in the next example, we're going to go ahead and show you how to define the coordinate system for turning in Visual CAM for SOLIDWORKS and orient the part. So I'll be switching over to SOLIDWORKS. And I have a part loaded inside of SOLIDWORKS. I'll switch from the mill module to the turn module in here. And as you notice, when I switch from mill to turn, the coordinate system is automatically oriented. In this case, the world X coordinate is oriented to the turn Z coordinates. You can see the blue arrow represents your Z axis, the green arrow represents the Y axis, and then the red arrow represents your X axis. So automatically the world X is swapped out with the turn Z, and the world Y is swapped out with the turn X. So the coordinate system has already been set up in here. However, if you take a look at this part, based on the orientation of this part, we need to make sure that the turn Z coordinate has to be along the axis of rotation of this part. So rather than having to rotate the part in your CAD system or having to remodel the part by picking a different sketch plane, you can go into defining the turn machine tool setup in Visual CAM for SolidWorks, and you can orient your machine tool coordinate system. So we would like to orient the coordinate system in here. So I'm going to use these spin angle controls, or I could use select surface or select planar curve, and any one of these choices in here, options to rotate the coordinate system. I'll use the spin angle. I'm going to rotate the coordinate system about the Y axis by 90 degrees. And you'll now notice that the turn Z coordinate system is oriented along the rotational axis. Now, once we've established the orientation for the turn coordinate system, in the next step, we would have to establish the coordinate system origin to the back face of the part to be able to define the part for turning. So I'm going to go back into the turn machine tool setup. In our machine tool coordinate system, I'm going to choose the coordinate system origin. I'll use the pick option in here, and I'm going to pick the center on the back face of the cylinder, and I'll pick OK. You'll now notice that the coordinate system origin is established to the back face. So we've established the coordinate system for turning and established the origin in here to program this part. In the next step, we would like to define the part. So currently the part has not been defined, and you can see it says part none. We'll click on part, and I'm going to choose select solid geometry instead of select curve, and I'll just highlight the solid model, accept my selections, and then save. So you'll now notice that the part has been defined, and the cross section of the part, the silhouette, automatically appears in your viewport. Folks, if you do have any questions in here at this point of time, please feel free to post your questions in the questions panel, and we'll do our best to answer them for you to help you in defining your part coordinate system for turning and also orienting the part. The next thing we'll be covering here is how to define stock geometries for turning. And we'll take a look at our visual CAD/CAM product first to start with, and then we'll look at RhinoCam, and we'll look at Visual CAM for SolidWorks as well. There's different stock ways you can define stock geometries in our turn module. So as you go into the stock types, we have cylinder stock, part cylinder stock, offset stock, revolve, and stock from selection. So once the part has been defined, selecting stock and cylinder stock will automatically compute the minimum bounding cylinder that is required to program this part. The stock radius and the stock length are automatically established. You could change each of these parameters in here. So if you need to do a face operation and you have additional stock that needs to be removed, I can specify the length and also the radius. Now, if you have some ID features on the part, and if your stock already has a hole or a bore on it, you could specify the length and the radius for the ID feature. So in this particular example, I'm going to set the inside radius to 0.5 and length is 0.1. And you'll notice that the stock, once it's defined, has an ID to it. And when you go into the Simulate tab, you'll be able to view the stock with the OD and the ID features on it. Now, we have different ways how you can display the stock. So you can display it as a full view, or you can do a 3/4 view of the stock display. So if you have features that have ID and you'd like to see it in the simulation, a 3/4 view might be a good way to display the stock in the simulation mode, or you could do a half or a quarter view as well. So these choices are available in our Turn module, whether you're running Visual CAD CAM, Rhino CAM, Visual CAM for SolidWorks, or even a Libre CAM. So this would be the cylinder stock type. And then we have what's called the part cylinder stock. So if you go down to stock, you can choose part cylinder stock. And this is similar to your part box stock or part cylinder stock, what you're familiar with in the mill module, where you can specify, in this example, you can specify a radial offset and also an axial offset. A radial offset allows you to increase the diameter of the stock that you're starting with. And an axial offset allows you to specify an additional length along the axis of rotation. So you can define the stock by defining a part bounding cylinder by specifying a radial offset and an axial offset. Now we will now take a look at a few other stock types in here. And this would be, we will look at how to define stock from selection and also stock from revolve stock. And for this, I'm going to go ahead and pull in another example to cover this in Visual CAD CAM. Again, folks, if you do have any questions, please feel free to post those questions in the questions panel, and we'll try to answer them for you. So for revolve stock and part offset stock, you could select or create a sketch geometry that could be modeled in Visual CAD CAM, or it could be imported from your CAD system in here. So in this particular example, I'm going to go ahead and define a revolve stock. So I've actually modeled a curved geometry in here. And this is just a 2D profile. So I'm going to pre-select this and go to stock and select revolve stock. So this basically revolves the curved cross section to define a revolve stock. You can view the stock in both full or 3/4 view. And there's the revolve stock defined. We could also define the stock as an offset stock by selecting a curved geometry to define an offset stock. I'm going to select a curve in here and define stock, offset stock, and you can specify a radial offset value, and that'll define an offset stock geometry. Now the other type of stock geometry you could create is a stock by selection. So you could have your stock modeled as a solid, or you could have it imported or created as a mesh, a pre-cut blank or stock geometry. You could pre-select it or highlight it and define stock using stock from selection. So we now have defined the stock using stock from selection, and you have your part. So to define the part, you can either select a solid, or you could select a surface, or even a mesh geometry to define your part. So the part is now defined, and so is the stock geometry.
One quick note: if you are bringing in a model stock, and one of the things that you might have noticed what Uday was doing with the layer manager is actually he's turning off the visibility of the part, or rather the stock model that you brought in. The reason he's doing that is obviously you don't want that model to participate in the programming. So you really need to turn that off. You can bring it in, select it as your stock model, and then once the stock model is created, you can turn off the visibility so it doesn't participate in the actual programming of the part. So thanks, Uday.
Thank you, Joe. So in Visual CAD and Rhino, you can use the layer manager to toggle the visibility of the part and the stock. We'll talk about how this can also be done in our plugin for SolidWorks. So we learned about the different stock types, creating a cylinder stock, part cylinder stock, revolve, offset, and stock from selections. We'll go ahead and take a look at the same in RhinoCam as well. So we've oriented the part and defined the part for turning. We'll define stock. We'll go down to cylinder stock. We could specify the radius and the length. So I'm going to set the radius to 1.4 and the length to 3.3. Now in this particular part, since we also have an ID feature, if you already had a pre-drilled hole or a bore, you can go back, edit your stock definition, and specify the inside radius. And your stock already has the pre-drilled hole. So the benefit of having a stock with a hole, if it's already pre-drilled, is when you do your roughing operations, it automatically knows that the hole has already been drilled, so you wouldn't be cutting any air as you program your toolpath. So the in-process stock, the stock geometry is taken into account when programming your toolpaths, and we'll get to that as we go through the turn demonstration today. So you can define stock using stock from part cylinder stock. So with the part cylinder stock, you will not be able to define an ID. If you have a bore or a hole in the ID, you wouldn't be able to do that with the part cylinder stock. So you'd have to go define it using the cylinder stock option. Now the offset and revolve stock works similar to how we did it inside of Visual CAD/CAM. So you could basically define your part geometry. You can pick up turn profile in here and specify stock using either revolve stock or a part offset stock. So there's your revolve stock. So basically you're selecting just a 2D profile and defining it as a revolve stock. We can select the same profile to define it as a offset stock in here. So you define your part for turning, and then you can go ahead and define your offset stock in here. So you need to pre-select your region before you define your offset stock. And you can specify the radial offset distance. So if you're working off a casting, then the offset stock would be beneficial in here. And the stock from selection works very similar to how we demonstrated in Visual CAD/CAM, where you can select a solid surface or a mesh geometry to define a stock from selection, and you can have it placed in a different layer and make the layer visible, define the stock, and then you can toggle off the layer visibility. Now folks, we'll take a look at the same in Visual CAM for SolidWorks for defining stock types. So I'll switch over to Visual CAM for SolidWorks, and we'll take a look at an example on defining stock using stock from selection. So in this particular example, I have modeled the stock and I've suppressed the feature inside of SolidWorks. So I'm going to go ahead and unsuppress this feature. I can select the feature from the feature tree and go over to the Visual CAM tab and choose stock and create a stock from selection. So once you have the feature highlighted, you can define your stock using stock from selection. And you'll now notice that the stock has been defined using the stock from selection, the solid geometry that we selected. And then in SolidWorks, since we do not have layers to toggle the visibility, we just go back and suppress this feature in here from the feature tree. So once you have the stock defined, we've suppressed the feature. And then we go through the process of defining the part. So you can define the part by selecting solid geometries, or you can define it by selecting a sketch geometry. So this is how you can define stock using stock from selection within SolidWorks. Now the process of creating cylinder stock and part cylinder stocks are very similar to how we created them in Visual CAD/CAM and RhinoCam, where you can specify the radius and the length. If the stock has a ID like a bore or a hole, you can specify the inner radius and the length as well. So just to summarize here, we talked about orienting part, defining the turn coordinate system, and creating different stock types. We are now ready to program some toolpaths. Now, before we program toolpaths, we'll look at how to define tools in turning. Folks, at this point of time, if you do have any questions, please feel free to post those questions in the questions panel, and we'll do our best to get them answered to you. Now, to define tools and programming toolpaths in turning, we'll first take a look at our standalone product, Visual CAD/CAM, and then we will look at RhinoCam and Visual Cam for SolidWorks as well. Now, if the Tools tab is not visible under the Machining Objects browser, from your machining browser, you can click on Tools Machining Objects to toggle the visibility of the Machining Objects browser. And under the Machining Objects browser, you can select Create Edit Turn Tools. And this will give you access to all the different turn tools as well as the tools for drilling for hole machining. There are different types of tools available in turning, like diamond inserts, triangular, circular, trigon, parallelogram, then grooving inserts, threading and parting off inserts as well. Now, to define an insert for turning, you have to define the tool type. So the insert type here would be a diamond insert, and you can specify the inscribed circle radius, the tip radius, the tip angle, the relief angle for the tool thickness, and you'd have to set the orientation for the tool depending on the direction from which you're going to be cutting. So you'd select an OD forward or an OD backward depending on which way you want the cutter, which way you want to be programming the part and how the cutter you want to approach. Now for the ID operations, you could choose ID forward, and we'll talk about these tool types as we program some toolpaths. Now, if you select the Help section from the Turn Help dialog, this gives you a description of each and every parameter that is available to you as you define tools for turning. So it talks about how to define or set the relief angle, your tip radius, your inscribed circle, and the tip angle. So selecting Help from the Help dialog, from the Turn Create Machining Operations dialog will automatically display the help files, and you can refer to each and every parameter, how to define them based on the tool and insert that you're going to be working with. So for turning tools, you would be defining the orientation, and you'd be defining and specifying the parameters. Now under the Properties tab, you can specify your tool number. The adjust register is used to set your offset number. Typically in turn programming, you might be outputting a tool number and an offset number. For example, it could be T0101 when you call out a tool or output a tool number and an offset number. So this would be specified under tool number, and the offset would be under the adjust register. So you could specify the CAD/CAM register and the coolant type that you'd like to use in your turn programming, and any additional comments. Now the Feeds and Speeds tab allows you to set the spindle either as a constant surface speed, which should be in units per minute. It could be inches per minute or millimeters per minute. And you can set the max RPM. Now the feed rates can be set either in inches per revolution or inches per minute. Or if you're working in millimeters, it could be millimeters per revolution or millimeter per minute. And you can set between constant surface speed or constant rotational speed, CSS or CRS. And the post can be configured to output whether it's going to be a G96 or a G97 for CSS or CRS. And you can specify IPR and IPM depending on the feed rate units that you'd like to program your toolpaths. Now we also have a load from file option, very similar to what you've seen in our mill modules, which helps you establish feeds and speeds based on the material type, the tool material, stock material, and the work diameter that you're working in, which is the diameter of your stock. And the maximum spindle speed and the cut feed rate parameters are automatically read from the post processor that you've selected as your current post. So this can give you a good reference or a starting point for establishing your feeds and speeds. So you can define tools, insert types based on each tool type, and also for each orientation. So I can have a tool that's defined for an orientation OD and one for ID. I can define it. So by selecting the orientation in here. Now once we have defined the tools in here, we're now ready to program some tool paths. So we'll look at how we can program it in our visual CAD/CAM product. So once we have the part defined, the stock has been defined. In the next step, we want to go ahead and establish our work zero, or which could be your program zero. Typically in turning, this is done at the rightmost face. So we do that by going to work zero, and we can choose pick. You can graphically pick a point or take advantage of the set to stock and set to part options. Choose set to stock box, and you can select rightmost face. So your X and Z 0 is automatically set to the rightmost face, and your X0 remains at the center of rotation. So all we're doing here is shifting the Z origin from the back face of the part to the rightmost face. You could either set it to the stock box, or if you want to set it to the finished face of the part, you could choose set to part box. So in this example, I'm going to choose set to stock box. And if you'd like to output this as your work offset, G54 or G55, you can select output work offset and specify the work offset register number. I'm going to choose generate.
Uday, somebody had a question about Z0 not being on the, on the face of the part. So this is exactly what Uday just showed, how to set the 0 to the face of the part, and hope that makes sense. Thank you.
So selecting set to part box sets the 0 to the face of the part. Stock box sets the 0 to the face of the stock. Generate. So now the work 0 is set. So you'll notice that when you click setup, the 0 is in the back face, and as you select work 0, the 0 is translated to the rightmost face or the front face of the part. Now let's go ahead and create a few toolpaths in here. So we're going to go into turning, and we'll pick roughing. So there are different types of operations you can program in turning, starting with roughing, finishing, groove, roughing and finishing, follow curve, threading, and parting off. So we'll start with the roughing operation. And in the roughing operation, you'll see that the available tool types for turn roughing are listed in here. So you could have different tools defined. You could have a drilling tool. You can have tools for threading, parting off. But for a turn roughing operation, these are the allowable tool types. As you go to Edit Select Tool, it automatically filters out the tool types based on the operation that you're programming. Very similar to how we have done in our milling product. So I'm going to choose the tool that says Diamond Insert OD. We'll set the feeds and speeds to be loaded from the tool. In the global parameters, you will notice that since the tool we selected has an orientation of OD, when the tool was defined, the orientation is set to OD forward. In the global parameters, you'll see that the approach type for the tool orientation, you can only either do an OD operation or a face. This means if you have a tool that's defined with an OD orientation, you will not be able to program an ID or inner diameter operation with the tool orientation set to OD. So the system automatically determines, based on the tool orientation, the approach type for cutting. So first, I would like to do a face operation to face the stock down to the face of the part. So I'm going to set the approach type to front facing. You can specify the tolerance and the stock to leave. We'll talk about the containment in a little while. You can specify your parameters for turn roughing. You can choose your cut pattern, could be linear, offset. You can add a cleanup pass, your depth per cut, control the entry and exit. Now all of these parameters are automatically set, the angle, the approach motion, the engage motion, based on the orientation that you select for the approach motion. So since we set it to front facing, this automatically sets these parameters for the approach angle. So you'll notice that the front facing that's generated here, it clears the stock that's on the front face, and also it programs the OD features as well in this particular example, you can see that when I run a simulation here, it does the front face and it continues to program the OD with the front face cut pattern. Now, most users would like to just limit this to the front face in here. So I'm going to show you how you can accomplish that easily in our turn product. So we're going to go back and edit the operation and go to global parameters. One of the ways you can avoid it is by selecting what's called a cut containment, and you can choose as simple as just picking 2 points. It draws a rectangle in here to establish the containment, and we'll generate this toolpath. So you'll now notice that the toolpath is just contained to the area that you specified, like a containment rectangle.
And another thing you should notice is this, it not only honors the containment, but also honors your stock model. So you can draw a box that's quite large, and the tool is not going to go and machine air. So it's not going to do air cutting. So it knows where the stock model is present, and it will only machine those areas. So it has full knowledge of the in-process stock model, if you will. Thank you.
Thank you, Joe. So the other way to program is, rather than using a containment rectangle, I could select what's called a select section to avoid areas from being machined. And in this particular example, I could just draw a section line. So anything that's past this is automatically ignored. And we'll talk about the benefit of using select sections in a different example here. So in this case, I chose a select section, and you'll notice that anything that's past the section is automatically ignored. So you could use this as your first operation to do the turn roughing for the face. Now, once the face has been roughed, I would like to go ahead and program the OD. So I'm going to do a copy paste of this operation. I could either do Control-C, Control-V, or right-click copy and right-click paste. And now I'm going to edit the next operation. I'm going to switch from face to outer diameter, and I'll remove these sections in here. And then you'll notice that when you go to entry and exit, the angles are automatically set based on the approach type. So when it's set to face, the angles are automatically set to 0. When it's set to OD, it's set to 45. You can go ahead and change it. So to make it easier for programming, it automatically sets the angles for entry, approach, engage, retract, and departure based on the approach type that you set it to OD, face, or ID. So now also I wanted to point out here is, since we did the roughing, the face roughing, when you do the turn roughing for the OD, it automatically knows the in-process stock, which means the material that's already being machined out and left from the previous step. So it's not cutting air on the OD roughing operation. The OD roughing operation is not machining the face that's already been cleared out. So in this particular example, we are using a linear cut pattern with a finish pass, and we've specified a stock to leave. So we programmed a turn face operation as roughing, and then a turn OD operation for roughing. The next thing we're going to add is a turn finishing operation in this example. We'll pick the same tool, and then in the global parameters, you can pick your start and end points to determine the direction of cut. So I'm going to choose select start and end points. Now notice that in the roughing operation, we actually drew either a rectangle or we could pick a section, a void section. In finishing, you just have to pick 2 points on the profile. So I could select, I want to start right here and go all the way to the end. So that determines the direction, you start and end. And if you'd like to add additional multiple passes for finishing, you can set it right here. And of course, you can change your entry and exit parameters. So we now have programmed the turn finishing operation. So we selected the start and end points. If I go back and reverse the start and end points, I could start from here, go down here. It's going to change the direction of cut. So it's going to start and go backwards. So we could choose the direction of cut. Folks, if you do have any questions, please feel free to post those questions in the questions panel. We will now go ahead and take a look at a similar programming workflow in RhinoCam, and we'll be more than happy to answer any questions that you may have. We'll talk about posting once we've done programming it with RhinoCam and also in VisualCam for SolidWorks as well. Okay, so we're going to now define the work zero since we already established the coordinate system orientation and defined the part. Very similar to how you've done in Visual CAD/CAM. You can set your work zero or the program zero to the face of the stock, rightmost face of the stock, or to the face of the part. So I'm going to pick set to stock and generate. Now in the next step, I'll program a roughing operation. So we'll go to turning and roughing. Now the tool definition would be very similar to what we did in Visual CAD/CAM, where you can define the insert tool type. In this case, we're defining a diamond insert, specifying the properties for the tool number, your offset number, coolant type, feeds and speeds. And once you have these established, you can go to Feeds and Speeds tab and select Load from Tool. In the global parameters, we'll first program a front face operation here. And I'm going to use the select section. And I would like to contain it. And I can use these object snaps in here to snap to the geometry. So all I'm creating is just a straight section to avoid for the front facing. So I want to exclude all the areas beneath it and then generate. So there's your roughing operation for the front face. We'll go ahead and run a simulation for that. Now in this example, I'm going to switch to a 3/4 view. So since we have some ID features, we're going to be programming as well. And as I pointed out earlier, it automatically takes into account the in-process stock. So it knows there is no stock material in here, and it's not generating a tool path or not cutting air as you notice it. Next, we're going to go ahead and program a turn OD operation, OD roughing. So I'm going to make a copy of this, do a Control-C, Control-V to copy paste, or you can do a right-click copy and paste. We'll edit this operation out. In the global parameters, I'm going to change from front facing to outer diameter. And I'm going to pick a containment section in here. And in this particular case, I'll pick a rectangle. So I only want to cut the front section. So I'll pick this as my containment. I'm just throwing in a large rectangle to specify my containment area. And then I'll choose generate. So you'll now notice that the roughing operation is contained in here, and it automatically takes into account the in-process stock as well. Now you also notice that based on the relief angle of the tool, it automatically protects and it's unable to cut all the way through on this groove feature on the model based on the relief angle that you'd set on a tool. So turn programming automatically checks for the relief angle protection and ensures that it does not gouge into the part. Now, if you want to program this feature as a separate grooving operation and you would like to avoid the turn roughing or finishing operation to not to cut into this feature, you can take advantage of the avoid section we talked about earlier. So you can go to global parameters, you can use select section, and you can pick an avoid section in here, and I can just pick these 2 points for an avoid section. So I've selected just a line by picking 2 points for my avoid section and then generate the tool path. You'll notice that now it's not cutting inside the groove. And let's go run a simulation in here.
Also, if you can show that relief angle being honored there so it doesn't interfere with the part. Absolutely. You can see that toolpath down there.
Sure. So I'm going to go back in here and I will exclude this section. I'll regenerate this path. And you can see that the relief angle is automatically honored in here, and the cutter is unable to get into the groove based on the tool relief angle. So if you change the relief angle, you might be able to cut slightly deeper into the groove on the model. So the system automatically accounts for the relief angle of the tool and ensures that it doesn't gouge into the part. So I'm going to go back and edit this operation in here again and add the avoid sections to it. So I can just select 2 points, use a select section, left click on the first point, and I'm taking advantage of the smart tracker in Rhino, so I can pick 2 points along the model in here. So basically you can just select 2 points in here to specify your avoid section areas and generate the toolpath. Now you can apply the same avoid section even on a finishing operation as well. So we'll go ahead and program a finishing operation in here. So I'm going to add a turning finishing. With the same tool orientation, we'll create a finishing path. We'll pick select start and end points. We'll generate the toolpath. And then we can also see that the relief angle is checked even on a finishing operation in here as well. Now let's go back and avoid that section by using global parameters. Use select section. You can just pick 2 points to avoid it and then select generate. And I'm going to run a simulation here. Now we will be programming these features that are on the back of this part in order to program the back of the part. And since you have your relief angle in here, you wouldn't be able to cut these features with the same orientation of the tool. So what we would want to do is we want to change the orientation of the tool. So we're going to add a new operation, turning roughing operation. And I'm going to create a new insert, and I'm going to call this OD backwards. And I'm going to switch the orientation from OD forward to backward, and I'll save this out as a new tool. So now I'm going to specify the tool to be used as OD backward. We'll program an OD operation in the approach type, and you can specify your parameters for roughing, your entry and exit. I'm going to add 90 degrees to it. So we'll basically be cutting, changing the entry and exit angles from 90 to 135, from 45 to 135, and we'll pick generate. So in this particular case, you'll notice that the tool will be approaching from the other side. So you can choose OD forward or OD backward to program these paths. The next step, we'll go ahead and add a finishing path with the same OD backward orientation tool, and we'll select the start and end points. And we can specify the entry and exit angles to be at 135. And generate the toolpath. So now that we programmed the OD operations, we'll go ahead and add a toolpath for the ID, and then we'll program the groove as well. So to program the ID, I'm going to go to hole machining. I can do a drill operation. If you need to increase the diameter of the bore from the pre-drilled hole that's already in there, you can specify the drill depth. I'm just going to select these 2 points. I can say add tooltip to drill depth, or you can even change the depth of the hole and then select generate. So this would create a drill operation, and you'll notice that since my my shank is going to collide with the stock material, it automatically notifies of a shank collision with the stock material, and it automatically flags the operation as dirty. And if you go into your toolpath viewer, it also shows that there's a shank collision in the toolpath viewer. So we program the ID operation, drill operation. The next step we want to do is an ID rough. We can select turning, roughing, and I'm going to choose a tool that's oriented to ID forward that's already in my tool library. Now, as you go into global parameters, you will notice that the approach type is set to ID, since the tool that you selected has an orientation of ID. So with the tool that's ID, you can program an OD or a face operation, so the system automatically determines that. And then you'll also check in the entry and exit, the angles are automatically set based on the approach type. Now generate creates your toolpath. I'm going to show the toolpath in the hidden area so you can actually see the toolpath for the ID, and we'll run a verification. So there's your cut material simulation. So it automatically takes into account the in-process stock, so it knows about the hole, the pre-drilled bore in the stock, the hole that you just drilled, and the ID roughing toolpath is computed based off the in-process stock and the material that's being left from the previous step. Now, once the ID is completed, roughing is completed, you can go back and add a finishing pass, very similar to how we did the OD finishing. You could pick the start and end points and then generate to create your ID finishing pass. Now, finally, we want to do this grooving operation in here. So we'll go to turning, and we can start with the groove roughing operation. And we have grooving insert tools. So in the case of grooving tools and parting off tools, you'd have to specify what is called a program point, or which could be your tool touch-off point. It could be set to left, or it could be set to center, or to the rightmost point. So when you define your tools, you can specify the tool touch-off point or the program point as you define your tools. And then you select a grooving tool for a grooving operation. In the parameters, you can specify the approach type. So you can, with the grooving tool, you can program an OD, ID, or a face operation. In this particular example, we're going to be doing an OD. And you have to pick 2 points, very similar to how we did for the finishing operation. You need to pick 2 points to represent the groove. So we'll pick point 1 and point 2 right here, the start and end points. In the roughing tab, you can specify the cut direction, your step over distance, your first plunge depth, and the subsequent depths in here when you're doing multiple. So it basically does like a peck operation. And you can also set your overlap distance in here and control the entry and exit parameters on your grooving operation and generate. So this creates a groove roughing operation, goes in multiple steps. And you can program a finishing operation using groove finishing to finish the stock material that was left from the previous operation in here. So we'll pick turn groove finishing OD, select the 2 points. And if you'd like to do multiple passes, you could do multiple cuts and set the entry and exit parameters. Generate. That creates your groove finishing operation. Now, once you have all of these operations programmed, you could take a look at the information. Right-click information gives you the estimated time. And in turning, you have an option to output in either diameter mode or radius mode before you post-process. So to set diameter mode output, you would need to go into preferences or CAM preferences and go to machining, and you have the option to choose diameter mode programming. So selecting diameter mode will basically scale the X coordinate value by factor of 2, so your output would be in diameter mode. So when I go ahead and select a post processor in here, for this example, I'll just pick a Haas post processor. You could just do an SL20 as an example here, and right click and post. And there's your posted output, and you'll see that the X coordinate values are all in diameter, so it's scaled by a factor of 2. Now the exact same settings is also available in Visual CAD/CAM, where you can go to CAM Preferences, Machining, and select Diameter Mode Programming. I'm going to go ahead and quickly go over this in Visual CAM for SOLIDWORKS as well on the programming workflow. So we've already defined our stock, and we've defined our part. I'm going to program the origin, which is going to be the work 0 to the rightmost face. We'll go to turning, roughing. We'll select a tool with the orientation set to OD. And then in the global parameters, you can choose the approach type, specify your depth per cut, and generate. So again, as we pointed out earlier, it automatically protects for the relief angle of the cutter. Now, if you want to avoid this section from being machined, you can edit the operation, go over to global parameters, and choose start and end section. I can just pick 2 points in here to represent the start and end section, and then generate the toolpath. So it'll automatically avoid the groove from being programmed on the roughing operation. I'm going to display the stock visibility in here and go back and run the simulation again. So once you're through with the roughing process, you could add a finishing operation. Set your start and end points for containment. And generate. Now, one thing I would like to point out in SolidWorks is if you want to pick a point or a containment that's outside the model area, then you may have to create a sketch in SolidWorks to be able to pick those points, because you can't snap to a vertex that's in space, or it's not within the model extents. So for example, if you had a facing operation that you're trying to program in here, and let's say my stock length was much larger, and you wanted to do a front facing with this part, but because you can't pick a point out in space, what you would have to do is you need to actually go ahead and insert a sketch in SolidWorks by just picking a face, create a sketch. And now the sketch could be as simple as just a line, an open geometry in here, and you can define that as your geometry for selecting the avoid section, and you can go into your roughing operation and use them for specifying your avoid regions when you're doing a facing operation in SolidWorks. So in Visual CAD/CAM and RhinoCAM, you wouldn't have to add or draw these additional sketch or line geometries or the curve geometries. However, in SolidWorks, you would have to do that because you wouldn't be able to pick or snap a point out in space. So we program the roughing and the finishing operation. Okay, now ready to post process. You can select the programming mode output to diameter mode programming. Right click and post. Generates your posted output file.